Okay, Andreas is an assistant professor in coding theory and cryptology at the Eindhoven University, and I will not take up any more of his time.
Inviting me. So I'm working not in coding theory, but really mostly in quantum cryptography. I guess why you're here is you heard about this quantum will kill everything. I want to take a step back and maybe discuss what actually breaks and how to fix it. So, who of you knows the difference between secret key cryptography and public key cryptography? Okay, that's half the room, so I will briefly go through it. So, in crypto, we've got two kinds of cryptography, or actually, we've got more kinds, but yes?
No? It's not muted anymore. Oh, someone turned it off. That's
Is better?
probably too much.
Too much.
That much? That's good. Yep. That's good? Okay. So, in secret key cryptography, whoop, that's too much. We've got, we use the same secret key for both parties that want to communicate. And then, for example, we can use secret key encryption, where Alice takes her plaintext, encrypts it with key K, and then Bob receives the resulting ciphertext and can decrypt it with the same key. And we've got means for authentication. So those are called message authentication codes that attach a tag which is generated with key K and also verified with the same key. Okay? Now, how do we build these schemes? In general, what we need is something that behaves like a random function, and then our attacks more or less boil down to unstructured search, or search in unstructured data. And so then the question is, how do we actually build functions that behave like random? Well, engineering. So we tend to call these people bit pushers. So they apply some statistical methods and try to mix stuff as cheap as possible, and then they get something which somehow behaves random. They do cryptanalysis, try to find things that are not random, and if they don't succeed in this, they assume this is kind of good. And so these things get weakened by quantum computers, but as far as we know, not totally broken. So we don't have any attacks that really break the schemes. However, this is actually something that I personally work in terms of research on, because a lot of things or a lot of results that we have about this topic actually don't carry over to the setting where we have quantum adversaries. Now, if we want to use this kind of crypto, the problem is, how does Bob actually learn the shared key K? All right? So that means we need some means to actually transport this key. And that's where public key cryptography comes into play. So in public key cryptography, every party has a pair of keys consisting of a public and a secret key. And the public key you can hand out to everyone as public information. The secret key you keep to yourself. And then, for example, for encryption, Bob can share his public key with everyone, including Alice. And then Alice can encrypt a message that can only be decrypted with Bob's secret key. That means as long as Bob keeps his secret key private, only he can decrypt the message. And so how can we use this to transport a key between Alice and Bob? Well, we encrypt the short secret key and then use that secret key to actually encrypt messages. Okay? And a second thing we can do with this is digital signatures, which are essentially replacing handwritten signatures. So for example, we use this to have third trusted parties write certificates that public keys belong to certain instances. Okay, so the applications of these two primitives are, on the one hand, especially code signing. So that's, I think, one of the most important applications. We are unable to produce working code. If you're using Ubuntu and you have a dual monitor setting, then you experience that this is a very hard thing to achieve consistently working. With every update, it's new fun, so we have to update our software. And you don't want some third party to send you an update that does whatever with your computer. So we sign these updates to make sure that they actually originate from the people that we want it to come from. And the second thing is communication security. So there we use some means to transport a shared secret key, so public key encryption or variants of this for short, so key exchange or key encapsulation mechanisms, and then digital signatures to actually authenticate the other entity. And so this is used in all our communication protocols like TLS, SSH, IPsec, and that's kind of the backbone of secure e-commerce, online banking, e-government, and also all kind of private online communication. Like if you use Signal, or for WhatsApp at least it's claimed, we cannot check this, but they claim to use actually secure protocols so that they cannot read in, and for this they also use this kind of crypto. Okay? And to exemplify the setting, because I want to make a point about this later, so how do we do communication security in general? The setting that we're concerned with is something where Alice, for example, decides at some point she wants to buy tea. So how does Alice buy tea? She goes on the internet and searches for a nice tea shop. And then at some point we'll find a shop, starts communicating with the shop, and then at some point has to pay. So you don't want to send your credit card data in the plane over the internet. So you start saying hi, then the tea shop will actually respond with its public key and a certificate by some commonly known authority which says, yes, this public key belongs to the tea shop. Then they use public key cryptography to establish a shared secret key. And afterwards, they use secret key cryptography to actually communicate. Okay? The order might have been unlucky. But how do we build this public key cryptography? Well, in general, we start from some computational hard problem. So we now, all these engineering approaches actually failed. So what people did is they started from the RSA problem or the discrete logarithm problem, and then built public key cryptography schemes. And then usually you've got a security proof which says, as long as this problem is hard, your scheme is secure. Actually, what you prove is, if someone could break the scheme, then that person could also solve the underlying hard problem. Good. Now the quantum threat. Why am I talking about this? So in the 90s, there were some put devil horns on this picture. This poor guy actually came up with an algorithm where he just recognized that quantum computers can do the fast Fourier transform pretty fast, pretty efficiently. And this can be used to find the period of a function. And if you find the period of a function, that's actually sufficient to factor efficiently, which allows you to break RSA, and also to compute discrete logarithms. So these steps are actually classical. That was something we already knew for a long time. The only thing that came from the quantum part was finding the period of a function. And if you got this, then you can apply already known algorithms. And so this actually breaks all the public key crypto that we currently got deployed on the internet. Okay? The problem is, to run this thing, you need a quantum computer which is large scale, so which has something like 2,000 qubits that actually are consistent. And I think you will hear about this in a bit more detail later, so I will not go into the details there. A second algorithm, which is not that harmful, is Grover's algorithm, and that allows you to do search in unstructured data and with a square root speed up. So if you want to search in an n-entry database, then you can do this in square root of n time. And this has applications to symmetric crypto, because if you remember what I said, all the attacks against symmetric crypto in general can be boiled down to search in unstructured data, as long as the primitives don't have any specific vulnerabilities. And the nice thing here is that we can actually prove that Grover's algorithm is optimal, at least for random functions. So you can show that this algorithm, that you cannot do better than this algorithm on a quantum computer. And so that means as long as our constructions don't have kind of inherent structural problems, which allows us to distinguish them from a random function or to show non-random behavior, we can just double the security parameter, so double our hash function length or double our secret key, and we're fine. OK, so what breaks if we can run these two algorithms? Well, these hard problems become easy. All right? These problems being easy means breaking our public key crypto schemes gets easy. And so if we get to this communication scenario, this first part actually gets easy to break. So this part where I'm establishing a shared secret key with a party that I never met before. All right? And the important part is, remember this, a party that I never met before. And I will come back to this in a moment. So why should we care about this today? In general, you might have heard about this quantum flagship in Europe. So Europe is investing $1 billion into building or developing quantum technologies. The US administration last year kind of matched this in terms of dollars. The Chinese have a similar program running, and you've got a bunch of industry partners that actually also try to play in this game. I mean, this whole quantum supremacy fuss, that's a different story, but they invest massive amounts of money, and so they assume they can make progress there. So this means at some point this just boils down to a question of risk assessment. I'm not saying these quantum computers will be built tomorrow, or we are already there because we've got quantum supremacy, which we, in my opinion, also don't have. But this might happen in 30 years. And I don't want to bet my personal data on this not happening. Because, and now, so if we assume this can happen, then we've got this problem. If you want to deploy cryptography in the real world, this is the most horrible thing ever. Well, we first have to have this whole part where we do research and essentially build the schemes and analyze the security, try to implement them securely. So this takes forever. Then at some point where we currently are in the post-quantum setting, we have to select systems and standardize them. This easily takes something like 4 to 5 years. And 4 to 5 years is then you're really fast. Then the systems have to be integrated into products. So if you want to use crypto, that essentially means they first have to get implemented in crypto libraries and crypto providers. Then these actually have to be rolled out. I don't remember how long it took. The J.H.A. actually made it into the Microsoft standard libraries. I think even 6 years after development, you wouldn't get this. So, and then at some point when these are out, you can actually use these libraries in your products and then roll this out. Right? So we're easily talking about a time span of 10 to 15 years. And that means we actually should move forward now, because there's one big problem. Even if we don't have quantum computers now, we are somewhat threatened by them. Because, of course, everything that we send over the internet now can, in theory, be stored and then be decrypted later. You've got no chance to get your hands on this again at some point and say, now we delete it. The internet doesn't forget, and especially the NSA doesn't forget. Right? I mean, who would store, build these kind of massive data centers to store all the data? Well, they actually got this on their own website, stating it's just 1.5 billion for these data centers where they store all the encrypted traffic, because at some point they might be able to decrypt it. And the second thing is, we are now building systems which are potentially out there for 30 years. If you think about satellites, they've got a development cycle of something like 10 to 15 years. And of course, if you build something for that amount of time, you don't want to waste it, kill it after a year. So you keep this running for a longer time. Similarly, if you design a car, the design cycle has something like 10 to 15 years, starting with the sensor nodes. And then the series will be produced for, and then be out on the streets for another 15 to 20 years. Right? So that means you already have to start thinking about this when you develop new products. And indeed, so ESA will be probably one of the first companies that, or not companies, but institutions that really look into rolling out post-quantum crypto for certain things productively. What about beating quantum with quantum? That's something that in the Netherlands gets hyped as hell. And okay, let's come back to this example. What did I say? What breaks? This part breaks, right? Talking to a person that you never saw before. What does QKD give you? The problem solved by QKD is as follows. Given an already shared classical secret, that's the point where I actually could stop talking because that was not the problem. That was not broken. You're solving a non-existing problem. Then, in addition, you require more than we required before because you need a physical channel between parties that support, essentially, that have the same hardware on both ends, right? I mean, I didn't try this, but I would bet if you have QKD hardware from different manufacturers, they will not work together. Well, and then what you can do is generate a longer shared classical secret. So that's something called key growing, which is fundamentally different from key establishment. So QKD just solves a different problem. I'm not saying QKD is useless. I'm just saying it's not the thing that fixes the problem that quantum computers might cause. So what would be the solution to this problem? Well, that's something that people started calling post-quantum cryptography. You can discuss if post-quantum is really the right term. There are other people call this quantum-safe cryptography. But that actually all goes into the same direction. So the idea is we actually still want to build public key cryptography, but for this we now use new computational problems which we assume are quantum hard, so which cannot be efficiently solved by quantum computers. Right? So that's the whole point. And people did research into this already before we knew about quantum computers, and the whole point was that people just analyze different kind of mathematical problems from which you might be able to build crypto. And so the more traditional areas are lattice-based cryptography, hash-based cryptography, multivariate and code-based cryptography. Somewhat recently, we added isogeny-based cryptography that's kind of based on elliptic curves and mappings between elliptic curves, but I will not go into the details. So that's kind of the thing that we were looking at for a long time and tried to build crypto from this, and I think we also were somewhat successful. Something that I consider the more modern approach to post-quantum cryptography goes a bit beyond this because it looks in general at a setting where users use cryptography on conventional computers but face quantum adversaries. And this actually means we have to not only look at new problems, but we also have to rethink how we argue about security. So how do we do formal security proofs? Especially this means, are our models still sound? So do we maybe have to change things there? And also, we have to look more into the complexity of actual quantum attacks. So before it was more like, yeah, these problems are hard to solve by quantum computers asymptotically, and then we look at the classical complexity of solving these computers, and by this we determine parameters. And now we move really to trying to estimate the complexity of attacks using quantum computers. And this all, in 2015, the NSA put out a statement that companies should not anymore migrate to elliptic curve cryptography, but should wait because there will be post-quantum cryptography that they should migrate to. And NIST already had a workshop on post-quantum cryptography earlier that year, and then at some point, I think this was not only 2016, I think already in 2015 announced that they will run some kind of competition. I think then in 2016 they actually officially announced the competition and to select post-quantum cryptography. And their role there is actually to manage a community process to actually select cryptography. That's how they see themselves. That's somewhat cheating because, of course, they are the ones that select in the end. We had a lot of discussions with NIST about making this public and making all information that they take into consideration in their decisions into the public. We cannot verify that they do this, but we can at least make sure that they take into account all our results that we have. That was too much. So what's the status of this competition? So the call ended in 2017, end of 2017. They collected 82 submissions. In December, then they put out 69 so-called complete and proper proposals. That only means these things all have a formally written specification. They have running, I'm not even sure if it had to run, but they have reference code. They had to include known answer tests. And so just these things were checked, nothing else. And it took us, a student of us, I think, 3 hours to actually break the first one of these submissions. So it was really, there was no thorough check in there. Like within 2 weeks, we had, I think, 6 of the submissions killed. So there was a lot of nonsense in there, but then there was also, the rest was essentially different variants of the schemes that we already knew in theory. So there were several different design decisions, like maybe how to tweak these things, which makes the process somewhat cumbersome. So NIST was a bit pushing towards mergers, which we tried to do for some schemes which are really close. And with the killed proposals, some sorted out by NIST because they were considered already at least scratched. They reduced this January, actually I think they published it in February because of the shutdown in the US. They reduced the competition to 26 proposals, essentially based on security, so that was the main selection criteria. And consisting of 17 CAMs, which are like public key encryption schemes to some extent, and 9 signature schemes. And currently, they still try to keep a spread over all the areas of post-quantum cryptography, like to not put all the eggs in one basket. And so there was a workshop in this year's August where the proposals were presented. The NIST already said, like, we might actually be happy with moving already forward with some schemes and standardizing them. But the community said, like, no, we actually want a second and a third round. And so the current plan will probably stick to draft standards existing in 2022. But I think NIST is pushing to really get out something early, possibly because they are afraid that industry just moves faster if they don't move. So what's the general issue in selecting things there? We've got this general conflict between security and performance. We've got some really conservative schemes which go back essentially to the origins of public key cryptography. So hash-based signatures, an area where I'm working, we only require security of hash functions, which is something we understand very well. And similarly, there are some code-based schemes which have a status almost similar to RSA in terms of maturity, but the sizes are, let's say, if you can avoid it, you probably want to avoid it. So, and then on the other hand, we've got all these schemes which have performance almost close to what we're used to today. But then we rely on security assumptions which are not really well tested. So for example, you're not relying on the hardness of breaking or solving certain problems on general lattices, but you're relying on the hardness of solving these problems over certain structured lattices, which are far less well understood than these general lattices. And so this is something where I think currently the competition has to find a decision, and also, of course, cryptanalysis will look more into these security assumptions. So now, like, the easy candidates are kicked out, and now you actually, it will get harder to break things. Yeah.
It makes me think of IoT devices. versus quantum computers. I mean, you need to do crypto in IoT devices that are not breakable by quantum computers.
You will, in certain cases, have to do quantum-safe cryptography on IoT devices, yes. That will come at a price. I mean, also now, most IoT devices actually do not want to deal with elliptic curve cryptography even, because they say it's too costly, right? Yeah. So for those, we will have the same problem as before. If you think about smart cards, this is not the biggest issue. Like, you can actually find schemes that run comfortably well on smart cards. There is actually a project that came out of the Pico Crypto project where Eindhoven and Nijmegen were involved, which is mainly driven by Peter Schwaber in Nijmegen now, called PQM4, where they look at the performance of all the NIST candidates on a M4 board. Cortex M4, I think. ARM Cortex M4, yes. So that might give some indication of what you can await there. During the workshop, actually, essentially two questions came out. One question goes into the integration, but another question that really popped up was proofs are complicated. And we really got an issue in the community that nowadays, I recently was on one of the program committees of our major conferences, and you get 20 papers, and then you read the first 15 pages, like the motivation really in detail, and then you arrive at the mathematical parts, and you're like, okay, I've got something like 2 hours maybe per paper, maybe 3. I cannot verify this whole proof. So what happens? Most of these proofs get actually published without too much verification. So we have quite some issues, and also naturally then in this competition, you see that we've got some proofs which are just in the wrong models. And this is actually something we still got somewhat in the open. There's, for example, the so-called random oracle model, in which many of the security proofs for classical cryptography are done when it comes to schemes that are really used in practice. And as the random oracle model, there models a cryptographic hash function, you have to give an adversary actually quantum assess to this in your proofs, because this is something that an adversary will be able to implement on his or her quantum computer, because it's just a hash function. So that leads to something called the quantum random oracle model, and if you still give proofs in the random oracle model, these are actually not saying anything about security against quantum adversaries anymore. The next thing is that we have proofs which are massively loose. There are people working on this, but if you have a relation which says, like, breaking this system is as hard as solving a lattice problem in a lattice of dimension 1,000 times smaller than the dimension used in your scheme, in most cases essentially means it's as hard as finding a vector, like a short vector in the 2-dimensional space, which is like nothing. So that doesn't mean that the things are easy to solve, but just you don't get any guarantees from the proof for actual parameters. Well, and then sometimes the proofs are just wrong, right? Those of you that followed the crypto news might have seen the whole thing about OCB2, where there was this one part in the proof where people were like, yeah, somehow this was bugging me, but I never had time to look into it. And the argument was somewhat hand-wavy, and yeah, turns out that you can entirely break the scheme, even if it has had a claimed security proof. And then in the post-quantum setting, we even have this problem that we have to deal with somewhat new math. So, I mean, currently, we prepare our students still with modular arithmetic for the crypto class. So that's the stuff that they actually know, but what they actually would need to know is linear algebra, for example, in large parts, which we do not actually teach them. So, and that's something that every one of us actually has to get into again. We have to deal with new models, which also makes the proofs a bit harder, and So on the one hand, models of computation and then models of security, which also just means we have to find new tools, and all this is, of course, very error-prone. And so this is really some issue at the moment. One possible way out, which we are currently hoping to get to, is something called computer-verified proofs. We at least have a computer that checks your proof. So you still have to write the proof yourself, but you use like logical verifiers to actually check that your reasoning is valid. There might be other ways. We were discussing a workshop where we battle our proofs, but I'm not sure if this will happen. The second thing, of course, is protocol integration. I didn't get into this in too much detail, but most of our protocols today are built around the Diffie-Hellman key exchange. And the Diffie-Hellman key exchange is something really beautiful that gives you something called the non-interactive key exchange. And that's something we don't have in a post-quantum setting so far. There is one isogeny-based candidate scheme which has very highly discussed security that comes from Eindhoven, so I cannot talk too badly about this. But I mean, also the designers would never suggest to use this now. This might be totally fine, but there's also a decent chance that this gets entirely broken in 20 years. So essentially, this means, especially in the NIST process, there is no candidate that can actually replace this. What we got are so-called key encapsulation mechanisms, which essentially simulate a way that you, or abstract a way that you actually use public key encryption only to encrypt shared secret keys. So what you do is, to make your design easier, you allow the encryption algorithm to actually select the shared secret and throw it out. So you've got a so-called encapsulation algorithm that takes the public key and it will generate a shared secret key for you, and an encapsulation of that shared secret key, so kind of an encryption of this, which you send to the other party, which can then be decapsulated to give the same shared secret. Yes?
Yeah, my question was, does that mean that there's no forward secrecy anymore until there is a Diffie-Hellman replacement?
No, Diffie-Hellman is not necessary for forward secrecy. You can, in theory, also get forward secrecy with RSA. It's just not used in practice, because we've got the Diffie-Hellman key exchanges, which are easier for this. I mean, you can just generate ephemeral key pairs and encrypt with those and throw away the keys afterwards. That gives you also forward secrecy. It's just somewhat cheaper with Diffie-Hellman. But the problem is with Diffie-Hellman, you can do a lot more because you've got a lot more mathematical structure, and that's something we currently do not directly have in a post-quantum setting, so we really have to rethink how to build our protocols. Also, there is an even bigger gap between the performance of secret key cryptography and public key cryptography. So in some cases, we might want to rethink when we use public key cryptography, is this really necessary, or might there actually be a way around where such that we can at least use more secret key cryptography? Yeah, especially because the efficient schemes that we got are actually less mature than today's crypto. And so this even increases the issue, because what most people now want to do is to build hybrid schemes where you, for example, there's an ongoing Google experiment where they try to use post-quantum crypto and TLS using an entry-based scheme that we designed, and they combined it with elliptic curve cryptography to make sure that even if the entry-based scheme fails, they still at least get the same security as they had before. So they don't lose security, all right? They will not make it worse. In the best case, they make it better. Yeah. There was a question.
Yes, the performance gap is what's is compared from the starting point like how it's now compared to a different type of encryption. But also computing power and the ways of computing may change in the future. Will that resolve this issue maybe? Or
well, that might resolve the issue. Indeed, like computing power gets better and better, and things get cheaper. But at the same time, our devices also get smaller and smaller. This whole IoT area, well, we try to build cheaper and cheaper things. And I mean, companies are mostly interested in also making these things cheaper. So as long, it's an annoying thing. Like since 5 or 6 years, I'm trying to get commands from companies saying like, this is the performance that we actually need or can deal with. And the command you only get is, well, not worse than today. And then you say like, yeah, this is something we cannot achieve, seemingly. I mean, there's some inherent problem that these problems which we build crypto from in post-quantum cryptography are all based on NP hard problems. So we cannot really use the NP hardness, but we use problems which are in general NP hard. And they all got a massive problem description. And that problem description has to appear somewhere, either in your public key or in your signature or in your ciphertext, but somewhere it has to appear, and this makes your sizes grow. Yeah, and today we already got a gap between secret key and public key cryptography, but this one will just get worse. Okay, I was surprisingly faster than I thought. To conclude, when we have a large-scale quantum computer, then we actually need new public key cryptography. We might already need it before for things that require kind of long-term security. I think in general, this is really a question of risk assessment when you want to start transitioning. We are making progress now to standardize our public key post-quantum cryptography, but we learned that we actually really still need some more time to do this right, because I think we will not get another shot. Like, this is now one chance to change some things, also in protocols, and now going too fast might probably be really harmful. If you have applications where you really require long-term secrecy, I mean, for example, your credit card data in 50 years, who cares? The card will be gone anyway, right? So the medical data of your child, if it has a statement that it might get a bad sickness when it is 50 and it's running for president at that point, might not be too good to get out. So for medical data, for example, you might want to rethink if you shouldn't start adding also maybe the clumsy post-quantum crypto that we already got. But this comes at a higher cost of performance. If you're interested in this, we started running a summer school on post-quantum cryptography. Next year, we will try actually to hold again a more one-week school with more focus on also doing exercises and so on. The year after, probably an executive school. You can also find all the submissions on the NIST webpage. There is a somewhat entertaining mailing list about the NIST competition, which might be worth following, where different topics, not only technical topics, but also some decision topics get discussed. And actually, on this site, you can also find videos from the last summer school. So there you can find slides, videos, and even exercises. That's it from my side, and I'm willing to take questions. There was, yeah.
Yeah, you say you may already want to start using post-quantum crypto now for highly sensitive data, even if it's bulky and imperfect. But are there actually tools to do that? Is it possible to use it in different environments?
That's not really our part as researchers, admittedly. We cannot maintain a productive library, so we put out public domain code, and indeed some projects start incorporating this code, but I think for this, it would actually be part of a company that maintains the code. So for example, there is code for McAleese and there's code for Sphinx, which you can easily use. And these are the somewhat more clumsy but long-term secure schemes, in my opinion. Yeah, but it's not, there's no library support for this in general. Yeah.
Can you go a bit more into the type of mathematics that is used in the post-quantum crypto? Like, is it still prime numbers? Is it still modal-based functions?
So we still got modulo because we've got size limited registers, not only for this. Most of it is linear algebra based. So in lattice-based cryptography, what you have is a lattice is a discrete set of points in space. And what you're asked to do is find a point close to the origin, given a really bad description of the lattice, like a really bad basis. And this can get arbitrarily hard. So this is really, I mean, you can get, if you have an almost orthogonal normalized basis, then this is trivial. But if you have something where the vectors are all but orthogonal and several are really long, then this really gets hard. In code-based cryptography, it's about decoding general codes. And well, for hash-based signatures, it's hardness of breaking a hash function, essentially. What am I missing? Ah, right. And then we've got MQ, where it's about solving multivariate quadratic equations. So you've got a system of equations in several variables, where all terms have at least 2 variables in there. At most 2 variables in there. And then you're looking for a solution. Yeah.
At this moment in time, everything is still done by like the human head to discover new methods. What does happen when AI meets quantum?
I think with machine learning, you will not find anything there. I mean,
I'm talking like really artificial intelligence, not machine learning. When the system gets really smarter than us humans.
ask the system. How should I know? I mean,
I think he will answer it.
probably it will come up with a blockchain. I would.
One or two questions.
I think I saw you first.
Semi-related. What will happen when governance meets quantum?
Well, this. What do you? In which direction do you mean this? I mean, governance. If
Well, the NSV is in that with the current cryptography, we have TLS 1.3, which should close some loopholes, but some people weren't really enthusiastic and decided we need to have a separate standard with a very misleading name, enterprise TLS, where it still could encrypt things after.
Well, I mean, that's something that post-quantum crypto will not change, right? We essentially replace the public key cryptography. What we do with it, like these problems will still be the same. There will not be any change in there. Like if you build a secure TLS version, let's say we go for TLS 1.4, or actually just add new cipher suits to TLS 1.3, then you will still have this enterprise TLS version.
But is quantum cryptography hard to subvert to such things, or just as equal?
So post-quantum cryptography, I think, is actually equal there. QKD has it essentially built in, right? Because currently you can only do point-to-point connections, and then you have to relink. So I mean, this is a government's wet dream. This is like, You essentially build in the way to listen in. That's, I mean, guess why they are funding it so hard.
Okay. What's the final question because we are running out of time. Thank you very much.